I want to take and hopefully in the next 18 minutes share some ideas, some information, give you one, I hope, take-home message, and perhaps a more abstract message, and that is the concept of feedbacks. So unlike the first talk of this afternoon by Dan Lieberman, where we talked about evolution, where an organism responds to its environment by adapting and evolving, I'm going to take a much broader picture view and think about, the oceans as a whole or the planet as a whole as well. And unlike evolution, which tends to be, forward-moving, always trying to, keep pace with the environment and changing, a planet or an ocean can't go in one direction. There's always got to be a reverse process. And so that's a fairly abstract concept. But I'm hoping it by the end of the next, now 17 minutes, that I'll actually be able to convince you that perhaps all is not lost and the world's not actually going all to heck. So I'm going to talk about the biological response in the ocean and in response to a changing ocean. And I'm going to do that through talking about this concept called the biological carbon pump. I'm going to show you some images of the diversity of plants that are so small you need microscopes to see them, and then talk about some of these feedbacks. So there's a range of models out there. I'm sure everyone's heard, and I'm sure most every day someone hears the word carbon. Carbon's the environmental chemistry of the planet. We think about carbon as it flows from rocks into the CO2 in the atmosphere. We hear about trading carbon credits. We hear about trying to reduce carbon emissions because we've linked it to climate warming. And my goal today isn't actually to talk and dwell about the pros and cons for that. It's to simply accept the fact that CO2 in our atmosphere, regardless of the mechanism, is accumulating, and that actually is having impacts on the planet as a whole. Everyone knows that the weather's getting warmer at some places anyway. We know that over the last 50 years or so, the planet on average is half a degree, 0.6 degrees warmer than it was back in the 1950s in World War II and right after World War II. We predict in the future it's going to be anywhere from 2 to 5 degrees warmer than it is now. And there's a variety of natural reasons for that. We have variable solar inputs. We have air-sea interactions like El Nino that are local to the Pacific but actually have a global impact in terms of impacting how the dominant weather system, the Atlantic, behave. We have the global ocean current system, not just the fairly localized upwelling system that Neil Burney just talked about, but the global mixing of nutrients from depth and heat from surface to bottom. We have volcanism. Overlaying all of that, we have all the human causes that we all talk about. Land use changes, release of particle aerosols. I don't know if any of you have ever seen my colleague Andrew Peters talk, but we have a monitoring station right out here on East Broadway, and you can actually see when everybody's sitting there in traffic during the week. And we have trace gases that, not the CO2 gases, but methanes and sulfur dioxides and things like that. That increase in the atmosphere is leading to an increase in temperature in the ocean, but the ocean isn't warming as fast. Perhaps that's thought of as a good thing, but in fact, because of the huge heat capacity of water, a little bit of warming goes a very long way. And so we really do have to be worried about this global circulation of water. It's not just the nutrients that come up from depth on a global scale, but if we've got to get that heat out. The ocean contains more exchangeable heat than any other entity on Earth. The land is not even close. If we don't get that heat somewhere, the atmosphere only warms up more. This is a positive feedback where the atmosphere gets warm because the water's warm. The water's warm makes the atmosphere warm, and we keep pumping in. As long as the sun's shining, this is keep going forward. Coincident with that is the other CO2 problem that we hear about. The other CO2 problem is ocean acidification. And again, I don't want to debate whether or not the CO2 in the atmosphere is going to be there anyway via a natural process or a human effect. But the fact of the matter is, if there's CO2 in the atmosphere, it's going to dissolve in the ocean. That's simple physics. We cannot deny that. What that means is that the ocean becomes more acidic. What that means is that as more CO2 dissolves in the ocean, more of that CO2 stays as CO2. And that's a very important point that I'll come back to in a second. So how do we evaluate that? So we have actually right here in our backyard in the Sargasso Sea, to the southeast, not to the southwest, but the southeast, we have a 20-some-odd year record that shows the CO2 in the ocean is increasing at the same rate as CO2 in the atmosphere, and pH going down. Now that has a large number of negative impacts. I mean, these are the kind of things that you hear in a lot of the popular literature. If you're a calcium carbonate or a mineral-bearing organism like a coral or a clam, or if you're in the Arctic, the heteropods and the pteropods, these things that most people have never seen in their lives, they're going to dissolve faster in an acidic ocean. You can't get around that. Has anyone ever put a little bit of eggshell in vinegar? Watch Mr. Wizard. Well, when I was a kid, so yeah, right? So minerals dissolve in acid. That's life. That's physics. We can't get around that. So a piece of coral in an acidic ocean is going to dissolve. There's no ifs, ands, or buts about it. They don't want to do that. They don't want to die. Does anyone here want to die? I don't. But, I mean, these organisms now spend all their energy trying to counter this natural physical process. And in the meantime, they're not growing, they're not reproducing, and therefore there's a very good likelihood a lot of these organisms are going to disappear. And that would be absolutely catastrophic. I've got a 9-month-old son and a 3-year-old daughter. I hope that when they're old enough to snorkel with sharks, that there'll actually still be a reef to see. But let's step back a minute, and let's take a slightly bigger picture point of view, and that there actually are positive things that we can associate with ocean acidification. Remember that I said that as CO2 dissolves in the ocean, more and more of it stays as CO2. That's a chemical thing. We won't get into that because equations put me to sleep when I was in high school, and I don't want to do the same to you guys. But as CO2 stays in the ocean, the biology, the single-cell plants, all of these guys, which actually produce half of the oxygen we breathe. So for the rest of the talk, I want everybody to take and only breathe half as fast. And that's what it would be like if biology in the ocean disappeared. But that biology is specific to taking up CO2 and making oxygen. It's not specific to taking up all the other chemical forms of carbon in the ocean. It's CO2. So ocean acidification makes more CO2. More CO2 actually enhances the organic growth rate of all of these plants. More oxygen, that's a pretty good thing. It means we can all climb Everest a lot faster. It also leads to carbon overproduction. And this is a very important concept with regard to the feedbacks, that many plants in the ocean actually can and do make extra carbon. They store it as starches and fats, just like I do, right? So I like to say I photosynthesize, but it's really just overeating and lack of exercise. But the idea is they do the same thing, and that's very important to keep in mind. So the idea I'd like to spread and sort of share with you and potentially convince you of today is that ocean biology, the plants in the ocean, to some degree, can and will counter ocean acidification, creating a negative feedback that will prevent the ocean from unilaterally becoming so warm nothing exists. So why the ocean? First, as I said, the ocean is the largest exchangeable body of heat. The ocean also holds most, except for the rocks we're standing on, holds the most exchangeable carbon dioxide. Both the ocean and the terrestrial biosphere take up massive amounts of carbon out of the atmosphere, but much of it returns in the time scale of a year. What makes the ocean unique is that a larger fraction, the difference between these two numbers relative to the difference between those two numbers is greater in the ocean. The reason that is, I must thank Neil Burney here for introducing the idea, is that, well, plants sink. They don't float. So they sink to the bottom. They regenerate or remineralize into the inorganic nutrients that then come up. So if the ocean were only yay deep, the ocean would be just as bad as the terrestrial biosphere. And that's what you have to remember is the soil's only so deep. In Bermuda, it's shallower, but most of the world, it's not so deep. The ocean is vastly, vastly deep. It holds carbon. So that's why the ocean is most important in the global carbon cycle. So how do the plants do that? So has anyone ever heard of photosynthesis? Excellent. You're better than most of my university students. So, sorry, I left the dot. So via the process of photosynthesis, ocean biology takes up 2 petagrams. Who's heard of petagrams? Excellent. Now we're right on par. So let's put that in normal terms. So 2 petagrams is actually about 200,000 pink Bermuda buses. So you can imagine spread out over the planet, littered liberally, 200,000 Bermuda pink buses to take in, who likes flying and paying airport fees? We just need to take these buses and stack them end to end. If we stack all these buses end to end, we now have a 2-lane highway to the US. So, okay, so hopefully that puts an idea of just how important ocean biology is. The reason it's important is this complex array of pathways and processes that take carbon from the atmosphere into that deep ocean. In total, this is called the biological carbon pump. But the biological carbon pump is not uniform across the planet. It would be nice if it was. I mean, if we could put a bus every, I don't know, square mile or so, it would be great, but it doesn't work that way. In fact, out here in the Sargasso Sea, where there's very little biology, we're actually better than a lot of other places at keeping carbon in the ocean. That's counterintuitive. You know, one would think the more biology, the more carbon in the ocean, but it doesn't actually work that way. So to figure it out, how do we do that? Well, that means that, you know, people like me have to jet set all over the world and, you know, go out when the weather stinks, I'll be honest. The weather's not too nice out here in the winter. Or where it's actually literally cold enough to freeze the moisture out of the air and you can't touch anything. And the first thing we see when we start looking at these plants, granted they're not as charismatic as sharks, but I think they're pretty cool. So are all these phytoplankton. So you have some that kind of look like, you know, the Space Needle a little bit, or maybe the Eiffel Tower that needs to go on Weight Watchers. You know, you see these organisms that have all these skeletons. These skeletons here that make these things unique are made out of minerals, minerals that may very well dissolve, and in some cases absolutely will dissolve in an acidic ocean. How big do you think these organisms are? Tiny. They're less than the thickness of someone's hair. I don't have that much, but less than the thickness of a human hair. These are the organisms that we're all told when we're young graduate students drive that carbon flow into the ocean. I'm growing up, luckily, in an era where we don't have to listen to our teachers. You know, we're allowed to second guess them. And actually, in the ocean here, the organisms that dominate are these small, tiny, tiny little things. These things are like 1/100th the thickness of your hair. These are what drive the biology out here in the Sargasso Sea and everywhere where you have purple on this globe. Where it's purple, there's no nutrients because those nutrients never make it to the surface. They're intercepted by the biology. And these organisms now, over 60% or 70% of the 70% of the ocean, become very, very important. So despite all that diversity between the large charismatic, relatively large charismatic phytoplankton and the small nondescript phytoplankton, they all contain carbon, they all contain nitrogen, they all contain phosphorus, just like all of our plants. And actually some interesting work by a pre-World War II oceanographer, Alfred Redfield, suggested that because the ratio of phosphorus to nitrogen in organic tissue is the same as the ratio of the nitrate and the phosphate deep in the ocean, that biology controls chemistry in the ocean. He was actually a chemist, so it warms my heart as a biologist to realize that even chemists are wrong. But we know that that's not actually the case. We know that if we take these organisms out of their environment, if we manipulate them, poke them, prod them, etc., they don't behave just like they do. And that leads to a whole other set of questions that I won't get into today, but just to think about the fact that biology in the ocean is variable, and if it's variable, that allows it to respond, and potentially that response can counter other stresses. So right about now, other than think I'm a quack, you probably are wondering how these things I've talked about so far work together to come up with this idea that I want to convey to you about how biology can counter ocean acidification. So just remember, we have ocean warming and stratification. As we put heat in the ocean, it doesn't mix. We don't get nutrients from below. We don't get heat out of the surface. Everything warms up. Because we have CO2 in the atmosphere, it has to dissolve in the surface ocean. Ocean acidification, we have this amazing range of diversity of phytoplankton, and we have this concept called the biological pump. So let's go back to a time when CO2 was actually more abundant in the ocean than it is now. So we just, how do you like that? I guess I forgot to change that one. So this is, imagine these are just little nondescript cells, or, you know, the prior biologist point of view. We go back 500 million years. That's a time when CO2 was about 10 times higher in the Earth-ocean system than it is now. It's a time when only these small, tiny, nondescript cells existed. All those big, charismatic, mineral-bearing phytoplankton didn't exist at that time. They only came on the scene about 200 million years ago. They came on the scene as the CO2 in the ocean atmosphere system was declining. As it declines, they become more abundant, more diverse, and these small little nondescript guys just sort of hang on and go with the flow. So, literally go with the flow. They're plankton, they can't swim. Sorry, bad joke. So let's start putting these puzzle pieces together, and I'm going to try to walk you through what I think are what my idea of the negative feedback. So, back when the ocean was warm and stratified and full of CO2, there were lots of cyanobacteria. These guys didn't exist. So that should tell us that under these conditions, things prevent them from growing. Well, if you're this guy, this is a coccolithophorid, it's a calcium carbonate, it's a clamshell, it dissolves. If it's dissolving, it ain't growing. So this guy's gone for sure in an acidic ocean. These guys, while they don't dissolve in an acidic ocean, because the diatom, the silicon dioxide, doesn't necessarily dissolve, without the nutrients that come with mixing, which we know doesn't happen in the stratification, they just simply can't survive. So these big guys go away when it's warm, stratified, and acidic, whereas the small cyanobacteria thrive and do well. So remember I said that we're taught as graduate students about yay tall that it's only the big cells that sink. It's only the big cells that drive the carbon export. Well, indeed, that's actually not the case. If you're willing to think outside the box and not believe what everybody tells you, that these small cells actually do contribute to the vertical movement of carbon, but they do so instead of these big, well-defined fecal pellets that come out of these guys, that these are these amorphous blobs. We call this marine snow because we're horribly uncreative as oceanographers. But these come from the fact that these cells are very, very good at producing too much carbon. It's a starch. They take and they exude it to their outside, just like I do. And they stick to each other. As they stick to each other, then they stick to other particles and another particle. All of a sudden, they go from this tiny cell that in and of itself can't sink to these very, very big amorphous aggregates that rocket to the bottom. So even though there's a lot more of these small cells will be in a future ocean, the biological pump isn't going to shut down. It's actually going to continue. And I would argue it's actually going to get even stronger because these are the types of organisms that actually can overproduce carbon. Think of it as sloppy in a sense. They're just fixing carbon. They got lots of sun. They got lots of CO2. May as well. It costs more to shut down your cellular machinery than it does to keep it running. So this is the feedback that I'd like to try to convince you of, that in a future ocean that's characterized by being warm, stratified, and acidic, the biological pump is going to increase, more carbon's going to go into the ocean, even though these big charismatic guys go away. So the question is, does that, do we see that in the real world? Because it's all well and good to think about these ideas, but is there evidence in the real world? So this is work also from our time series station over the last 20 years, just out here, the southeast of the island. Over the last 20 years, we've seen more of these small little guys in the ocean. The particles that they produce are becoming more and more carbon rich. They're deviating from this constant ratio more and more with time. And actually, there's more and more carbon leaving the surface ocean with time. So I would argue that at least over my lifespan so far, that we have more cyanobacteria, they're more carbon rich, and they're actually sinking out of the ocean. Potential evidence that the biological carbon pump is providing a negative feedback to counter ocean acidification over the course of time. So I'll leave you with this. I don't think all is lost. The biological pump's not going to offset everything, but it'll offset something. And we have to accept the fact that the planet and the oceans have to have a return process, and they've got that built in. There's natural resiliency in organisms and marine ecosystems. And while we absolutely need to study carbon and find ways to reduce our carbon emissions from human effects, we also need to study the natural mechanisms in ecosystems to figure out how they're responding. 70% of the planet is water. 99% of the livable space on planet Earth is actually water. So it really should be planet ocean. That's not my phrase. That's a lot of people's phrases. But the fact of the matter is we need to understand how these marine systems function, how they respond to stresses, because they may very well have already figured it out while we're sitting here scratching our heads trying to say, well, we're going to solve this by. And I'll leave it at that. Thank you.